So let's do a different example. Let's do a rational function. So let's consider that we have the rational function f of x is equal to x squared minus 1 over x to the fourth minus 1. Now, for this function, the first thing that we want to do is we want to consider its domain. And since we're dealing with a rational function here, we want to be very careful that our denominator is never 0. So we want to make sure that our denominator here can never equal 0. So to avoid that, we set it equal to 0 and we solve. So hopefully you can tell that right away, the thing that's going to cause this to be 0 is that if x is equal to plus or minus 1. So we want to exclude x equals plus or minus 1 from the domain. So that's what we'll go ahead and do. So we'll say that x cannot equal plus or minus 1. So this is a good thing to keep in mind for our function. And you know that at the end of the day, we're going to be graphing it. So it's a good idea to maybe make an XY table. I usually zoom in a lot more and you guys can't see me zooming in, but I'm using a different way for doing this. So unfortunately, this is what's going to happen. Okay, so I'll just graph my XY here. Y, X. Okay, so there's my domain. Now my second step is to find my intercepts. And remember, for our intercepts, we have two different types of intercepts. We have x-intercepts and we have y-intercepts. And so for x-intercepts, our job is to take our function and set it equal to 0 because you want y to equal 0 at that point. So we're going to set x squared minus 1 all over x to the fourth minus 1 equal to 0. And so the only thing that's going to cause this being 0 is if we have the top equaling 0. So if I set the top equal to 0, notice that I'm going to get x equals plus or minus 1. But here's a problem. This actually cannot happen because in our domain, we restricted that we could not have x equaling plus or minus 1. So we need to take that out. So actually, this one will have no x-intercepts. Because it's not possible, because what did end up having an x-intercept caused our domain, what we did end up getting for our x-intercept caused domain issues. So we don't want that. And so for our y-intercepts, what we need to do is set x equal to 0. So we'll make this 0 and we'll make this 0, which will cause your y-intercept to just be negative 1 over 1, which means that it's just 1. So your y-intercept is 1. So that means that this one here is 0, 1. Which is good because now that tells us that we have a point at 0, 1. So if we make this, just to make this graph a little bit bigger, I'm going to make this 1/2 and then make this part 1. So at 0, 1, I'm going to have a point in our function. So good to start kind of plugging things in as we know it. And for our domain, we know that at, let's call this -1 and +1, that something funny is going to happen there. Now, whether it's an asymptote or whether it's a hole, we don't know just yet. But that's the next thing that we're going to actually figure out, our asymptotes and our holes. So we want to see if we have any of those. And I'm just outlining this for you. You don't have to do it like this each exact time. If you know how to kind of navigate through these different functions, and don't really bother too much with this part. So for our asymptotes and our holes, two ways we can do this. We can use our limit notation, of course, but you have so many tools. So I want you to use whatever is easiest, right? Because that's a part of being a mathematician, is you have all these tools in your belt. Yes, you can use limit notation, or you can go ahead and just use what you've learned from algebra if that's the way that you remember it best, or you can do a combination of the two, whatever it is that you like. But for our asymptotes and our holes, remember that for our asymptotes here, what we want to do is, for our vertical asymptotes at least, let me write this down. Whether there is or isn't any, happens when the denominator is equal to 0. And it doesn't cancel out with the top or the bottom. So that means that we might want to do some factoring here. And maybe when you first seen this problem, you wanted to factor. And that's a good habit. You should factor. And so if I look at this function, I want to factor the top to be x plus 1, x minus 1, because I have the difference of 2 squares. And then down here, I also have the difference of 2 squares. And so my difference of 2 squares here is x squared minus 1, x squared plus 1, because I had a 4th power here. And now here I have another difference of 2 squares, so I go ahead and factor that, and I get x plus 1, x minus 1 at the top, nothing changes there. And then I get x minus 1, x plus 1 for my difference of 2 squares from that first piece, and then the second piece stays the same. So I get x squared plus 1. And then now I notice that, hey, this cancels with this cancels with this. And at the end, you're kind of just left with 1 over x squared plus 1. But remember, because these canceled out right over here, those give us what's called a removable discontinuity. Or holes. So we have holes in our graph now, and we're able to actually figure that out. And so the only thing that's left in the denominator is this x squared plus 1. But no matter what I put into that, I'm never going to get 0. So I actually don't have any asymptotes. Nothing will ever make it 0, because this x squared will always be positive, plus 1 will always be greater than 0, no matter what I plug into that. So there's actually no vertical asymptotes for here. Now, if it would have been the case where I went up here and these didn't cancel out, then these would have caused those vertical asymptotes, but they're gone, they're away, and now we're just left with this simplified version of the graph. Now, there's a reason I didn't do this at the very beginning, was because I wanted to talk about the domain. And so if you go ahead and jump from here to here, then what's going to happen is you might not get that in your domain. You cannot have plus or minus 1. And that's really important, because it looks like these are actually going to give us our holes. And I'll show you how to find your holes in just 1 second. So we figured out there's no vertical asymptotes, but now that we know that there's no vertical asymptotes, we can actually find the holes, and the holes are actually going to come from this simplified version of our function. So what happens here is that, yes, in your domain, you can't have plus or minus 1, but you know that the holes are going to happen at x equals 1 and at x equals negative 1. We know that for sure that's going to happen because they canceled out. They're removable discontinuities. So now what we want to do is plug in 1 into the simplified version, and that's going to tell us the point on where that hole actually is. So if you plug in 1 into this function here, you'll get 1 over 1 squared plus 1, which is positive 1/2. And if you plug in negative 1, you'll get the same value. You get positive 1/2. And so that means that 1/2 will have a hole. So at negative 1/2, we have a hole, and at 1/2, we have a hole. So we have holes right there. And so these are all the tools that are helping us find our function. Now for our horizontal asymptote, what you want to do here is you want to actually look at what's happening with your function. So we've learned a few things here and there about our function. about finding horizontal asymptotes. And remember that in our class, or in your 125 class, you might have learned that, hey, our horizontal asymptotes happen if the degree of the top is less than the degree of the bottom, then you have a horizontal asymptote at x equals 0. Okay. The way that we did it in this class was we looked at the long run behavior of our function. So what we want to do for our horizontal, so if we want to look at our horizontal asymptotes, we want to look at the long run behavior of our as x goes to negative infinity or as x goes to positive infinity. Or you could remember that from your algebra class that if your denominator degree was greater than the degree of your numerator, so if we're looking at this, if this was greater than, this is like the shortcut, right? But if this was greater than this, then what we would do is that the horizontal asymptote is equal to y equals 0. So I know that it's going to equal y equals 0, but what if you instead, since we know L'Hopital's rule, we actually used our limit notation and said, if we take the limit as x approaches infinity of f of x, which f of x is x squared minus 1 over x to the 4th minus 1, then what do we get? So the first thing is that if you plug in infinity, you'll get basically infinity over infinity. Now remember that when you're evaluating functions to infinity, we want to consider which one goes to infinity faster. And for sure, this one's going to go to infinity faster, but if you forgot that, right, we'll end up with an undeterminate form, which is infinity over infinity. And so remember, this is really good practice for your final that we can apply L'Hopital's rule. And then after that, so if we apply L'Hopital's rule, then we'll get the limit as x approaches infinity. And then we'll take the derivative of the top and the derivative of the bottom. The derivative of the top is just 2x. And then the derivative of the bottom is just 4x cubed. We plug in infinity again, and we get infinity over infinity. Oh, that means we can do L'Hopital's rule one more time. And so if I apply L'Hopital's rule one more time, I get the limit as x approaches infinity of 2 over 12x squared. And then this tells us that it's going to be 2 over infinity. And remember, a number over infinity is just 0. So your horizontal asymptote is y equals 0. So that tells us that we have a horizontal asymptote at y equals 0. So let me draw that in. This is your horizontal asymptote. That's ugly. Y equals 0. But we're not done. We still need to, we maybe have a feeling of what this graph looks like by the points already, but we still want to know, is there any critical points? And you could probably already see about one of them, but we still want to check them out. So our next step is, and I'll move on to the next page. I probably should have graphed this in the next page, but let me go ahead and cut this and move it to the next page. And so our next goal is actually going to be to find our critical points. So let's do step 4, and let's find our critical points. Okay, so do me a huge favor, pause the video and try to find the critical points yourself and actually test your intervals of increasing and decreasing, because I think it'll be really good for you to practice doing that. So remember that to find the critical points, you want to take your derivative of your function and set it equal to 0. So let's go ahead and do that. We're going to take our derivative, which is f prime of x, and that's going to end up equaling negative 2x over x squared plus 1 all squared. So hopefully everybody got that. And we want to know when this is equal to 0 because that's what's going to get us our critical points. Okay, perfect. So now after this, so hopefully you can see that from here, what's going to cause your derivative to be 0 is this piece right here, because if the numerator is equal to 0, then your whole function will be equal to 0. So your critical point is x equals 0, which seems like something that might happen because it looks like your function looks like it might do something like this. Probably, maybe. We're not sure yet though. We still need to do a little bit more work. And so after we find our critical points, we need to test them on an interval to determine whether our function is, where our function is increasing or where our function is decreasing. So let's go ahead and do that. Okay. So hopefully you were able to test the points yourself as well. These are all good habits. And so we test our critical point 0. No. We still need to do 2 more critical points. And remember that our critical points happen where our derivative is not differentiable. Something just fell. Okay. So our derivatives happen, our critical points happen where our function is not differentiable. So we need to check also -1 and 1. Because although it might seem like it's not different, I mean, it is differentiable here, it's actually not, because our function is not continuous at these spots. And remember, we can't take a derivative of something if it's not continuous there. So those are also critical points as well. So these are all good things to know. And so now hopefully you can test points. So you are welcome to test whatever you want. Remember that we're testing at our derivative here. And so hopefully you did this, and then you would see that here we begin to increase, and here we begin to increase, and here we begin to decrease and decrease. Remember, it's kind of easy to tell because over here we're negative on the number line, and the denominator again is only going to be positive, and the numerator is what's going to cause our sign to change. We have a -2x, so whenever we plug in a negative value for our x value, this is going to cause this to be positive. And so that's why on anything on the left-hand side of 0 is going to be positive, and anything to the right is going to be negative. So that means that here we are actually increasing, and here we are decreasing. Okay, but we still need to check -1 and +1 to make sure there's no change of behavior there. And so now we know that we are increasing from -infinity to -1, union -1 to 0. And we don't want to just say -infinity to 0 because it's not defined at -1. There's nothing there. So we have to be careful when we're writing that. And then we are decreasing from 0 to 1, union 1 to infinity. And now from here, we can go ahead and find our critical points. And so from the picture here, we can tell we're going to have a maximum at x equals 0. And we have a real max at x equals 0. And that happens at +1. So our maximum is at 0, +1, which is what we expected by the shape of this graph here. Okay, and we already have that plotted, so we don't have to plot it again. And now the next thing we want to know is about our inflection points. And for our inflection points, we actually just want to take the second derivative of our function, f prime of x. So go ahead and take the second derivative of that. And it's a little bit more complicated because the first derivative is a rational function. And so that means that we have to do quotient rule all over again. But it's okay, it's not that bad. So go ahead and pause the video and try it for yourself. And hopefully you leave the denominator alone, take the derivative of the top, minus the top, times the derivative of the bottom, which is 2 times x squared plus 1 times another 2x, all over x squared plus 1 to the 4th power. So hopefully you got that. And then we can simplify this a little bit. If we simplify this, we'll end up with, so we can factor out a -2, and we can also factor out this x squared plus 1 because we have it on both ends. And so we end up with x squared plus 1, and we factor that out. We're just left with x squared plus 1 at that spot, minus, and then here we factored out a -2. So we'll end up with 4x squared. So hopefully you got that. And then all over x squared plus 1, all to the 4th. And so now this goes away with this one. And so we're left with -2 times. And then here, so we factored out a -2. And now we're left with -2. And then you can combine x squared and this -4x squared together, and then you're left with -3x squared plus 1 all over x squared plus 1 all cubed. Okay, perfect. And now after that, we can simplify just a tad bit more, and we'll end up with 6x squared plus 2 all over x squared plus 1 cubed. So this is our second derivative. And remember that for our second derivative, in order to find the inflection points, we need to set it equal to 0. And when we do that, you should end up with x equaling plus or minus √3/3, which is approximately plus or minus 0.58. So hopefully you got that as well. So these are our inflection points, and now we want to test for concavity. So let's go ahead and test for concavity. And to test for concavity, we need to do the same thing we do for that first derivative test, but now we're testing on √3, -√3, and then positive √3, 3. So go ahead and pause the video and test these out yourself, and then I'll go ahead and try them with you as well. But also still remember that if you're not differentiable at -1 or +1, we still need to check. I mean, if you're not differentiable at -1 or +1, then you're not going to be differentiable on the second derivative at those points as well. So then we also still need to test -1 and then +1. So go ahead and test those as well. So you're going to need to play around a little bit more, but hopefully you are able to get that. Okay, perfect. So then here, this is what I got. I got that I was concave up here, concave down, concave up, and then concave up as well. So that's going to help us graph our function, but it's a good idea to go ahead and write your intervals of concavity. So go ahead and do that. So your intervals of concavity are, so we are concave up from -1 to -√3, 3, union √3 over 3, 1. And now, oh, wait, sorry. So we are concave up from -∞ to -1, union -1, √3 over 3, union √3, over 3, comma 1, union 1, comma infinity. And then we are concave down from negative root 3 over 3, comma root 3 over 3. So if we look here, what it's saying that our graph here from negative infinity to 1, we are concave up. And then root 3, comma root 3 is roughly 0.58. So somewhere right here, it starts changing to concave down. And then from somewhere over here, it also starts changing back to concave up again. So our graph looks something like that. I mean, it's kind of ugly, but it looks something like that. And our inflection point are these points here, root 3 over negative root 3 over 3 and positive root 3 over 3. So in order to find those points, we just plug those points back into our function, and that's what's going to tell us our inflection points. So plug those in, and those should give you something about right here to where your inflection points are. So this is basically how you use everything that you've learned in calculus in order to graph functions.